Hi. There are several ways to generate Pythagorean triples, and here's, I think, my favorite. Um, the video by Michael Penn is maybe the more standard one, but here's how you can generate them. You're going to consider actually a geometric problem for a second, and that's to find the intersection of the unit circle, x squared plus y squared equals 1, and the line y equals mx plus 1, which has slope m and passes through the point -1, 0. And specifically, we're going to be concerned with the case where the slope is strictly between 0 and 1, and what's going to happen then is, as you vary m, as you can see, the intersection of this line with the circle, besides the constant point -1, 0, is going to be a point on the first quadrant. Okay, so we go as far as 0, almost 0, and we're down at 0 at 1, 0, and up to 1 takes us to 0, 1. But we want to consider numbers strictly between 0 and 1. Okay, so let's take a look at this intersection point as a function of m. So I'll switch over to the document camera. So here's the two curves, the curve and the line that we want to intersect. Okay, so it's just some standard algebra. We're going to substitute in place of y m times x plus 1 into the equation of the circle. And when we do that, we can rearrange the terms so that we have a quadratic polynomial. Okay. M squared plus 1 is the coefficient of x squared, 2m squared of x, and the constant is m squared minus 1. Now we know this quadratic has one root of -1. So we're going to use synthetic geometry, synthetic division, to do the division. You're going to divide x plus 1 into this polynomial. And if you're familiar with synthetic division, that's the same as evaluating this polynomial at -1. Okay, so I assume you've seen this. Basically, you take the first coefficient, bring it down, multiply by -1, add, multiply by -1, add, and the fact that we get 0 here is an indicator that the -1 is a root. But not only that, but m squared plus 1 and m squared minus 1 are the coefficients of x and the constant term in the quotient. Okay, so that's really what we want. So we can factor our original polynomial into x plus 1 times m squared plus 1 times x plus m squared minus 1. So there's x. We can solve for x now. The x coordinate is by setting this equal to 0. And we get this. We can substitute that x value into the formula for y, the line, and it simplifies to this. So x is 1 minus m squared divided by 1 plus m squared. Y is 2m over m squared plus 1, which is 1 plus m squared. Okay, so there's the second point of intersection. Now, what we want to do at this stage is make the observation that if we set m to be a rational number, then x and y will be rational. Not only that, but if we pick a point that's rational on the line, on the circle, and connect it up with -1, 0, point -1, 0, the slope will also be rational. So, in other words, the point of intersection of the line with the circle is a rational point. In other words, the x and y coordinates are both rational numbers if and only if the slope is rational. So we're going to set m to be a rational number. So at m equal rational number, we're interested in assuming that the rational number is reduced to lowest terms, so the GCD of a and b is 1. We also, assuming that the slope is between 0 and 1, so b would have to be greater than a. And we make that substitution. And it looks like this. But if we multiply the numerator and denominator in both coordinates by b squared, things simplify a bit. You get this. Okay, so that's, in terms of a and b, those are the coordinates. And since this is a point on the circle, we know that this x coordinate squared plus the y coordinate squared is 1. We get this equation here. But if we multiply through by b squared plus a squared, we see that we get a Pythagorean triple. Remember, a and b are integers. So this is a Pythagorean triple. It's b squared minus a squared, 2ab, and b squared plus a squared. Now we have to make one additional condition to make sure it's a primitive Pythagorean triple. Besides the assumption that a and b are relatively prime, we have to assume that a and b are not congruent mod 2. So in other words, they're both, one's odd and one's even. In other words, if both of them are odd, or if both of them are even, then the three numbers b squared minus a squared, 2ab, and b squared plus a squared would all be even. And we want ones that are not, have no common factor. So that's a characterization. We can generate Pythagorean triples from that. So I'm going to go back to the Mathematica document. Now, as I was doing this, I was allowing m to vary, but using the slider, I get floating point numbers. But I can substitute a value. So let's take 4/9, for example. Notice that 4/9 produces this this triple, the 9 here. The two things kind of get smushed together here, but 65, 72, and 97 is a Pythagorean triple. We can get some of the more common ones by looking at 1/2, I think, for example. 1/2 gives you the 3, 4, 5. Poor design to not put these two things together. But every possibility where we take a numerator like 32 and a denominator that happens to be greater than 32 and not have a common factor with it, and has to be odd, 67, for example, produces a Pythagorean triple. So if you like to do it this way, you can generate any Pythagorean triple. That's it. Hope you enjoyed this.